Let us understand the basic concept of frequency domain, polar plot and Nyquist stability criteria. After learning this particular lecture video, you will be able to have a quick start of polar plot and Nyquist stability criteria. Let us discuss first the frequency response of closed loop systems. We know that we have seen in case of time response is nothing but a variation of output with respect to time. In a similar way, frequency response is nothing but a variation of magnitude and phase for a sinusoidal input with respect to change in frequency, which we call it as a frequency sweep. And the transfer function of the closed loop system, it can be expressed as shown in this particular figure. Here m of s is nothing but gs closed loop transfer function, that is nothing but y of s by r of s is g of s upon 1 plus gs hs. Under the sinusoidal steady state, in case of frequency domain, we substitute s is equal to j omega, sigma is equal to 0. As s is the complex function of sigma plus j omega, we substitute sigma is equal to 0 and we obtain the sinusoidal closed loop transfer function, which we call it as m of j omega, which is equal to y of j omega upon r of j omega, that is g of j omega divided by 1 plus g of j omega h of j omega. And m of j omega we can express in terms of magnitude of m of j omega and angle m of j omega. Okay, so angle is calculated as the angle contributed by the zeros minus angle contributed by the poles. Now let us see what are the frequency domain specifications. There are various frequency domain specifications. Among them, we will discuss first few of the specifications that may be needed. First of all, let us see, this is the variation of the output, that is nothing but magnitude of m with respect to the frequency. And this frequency curve is like a resonance curve, and there is one frequency at which the curve is having its peak, that we call it as a resonant peak. The frequency we call it as a frequency at resonant peak, that is nothing but omega r. And phase is typically like this. The phase is for minimum phase systems or for proper transfer function, the phase is reducing with respect to frequency. Now the resonant peak mr and bandwidth, which we define it as the frequency at which the magnitude of j omega drops to 0.707% or 3 dB decibels down from its zero frequency value. Okay, so this is the bandwidth, and this particular slope is called as cutoff rate. The frequency domain is having certain advantages with respect to time domain that we can understand from the filter characteristics, whether it is a high pass filter, it is going to increase the noise, or it is a low pass filter, it is going to reduce the noise. And one important thing in case of linear system is the time domain and frequency domain specifications are correlated to each other. For example, the resonant peak MR is correlated to damping ratio zeta with the relation MR is equal to 1 upon twice zeta square root 1 minus zeta square. This is true for zeta less than equal to 0.707. That is, higher the value of damping ratio zeta, lower is the resonant peak. Bandwidth is also correlated directly to the omega n. Omega n in turn is 4 by zeta omega n. So, TS is equal to 4 upon zeta omega n, and his bandwidth is directly correlated to omega n. That is, if omega n is higher, the speed of response will be faster and bandwidth will be higher. Okay, so higher bandwidth means higher speed of response, and it is correlated by this particular expression omega n 1 minus 2 zeta square plus square root of 4 zeta to the power 4 minus 4 zeta square plus 2 and to the power 1 by 2 whole to the power 1 by 2, and omega r is nothing but omega n square root 1 minus 2 zeta square. Okay, so these are the few frequency response specifications. The another important frequency response specifications are gain margin and phase margin, that we can only understand after the introduction of the Nyquist stability criteria or after we introduce the Nyquist plot. So to start with, these are the frequency domain specifications. Now let us move towards polar plot. The polar plot of a sinusoidal transfer function is a plot of magnitude of g of j omega with respect to the phase angle of g of j omega on the polar coordinates as omega is varied from 0 to infinity. Why it is called polar? Because it represents the polar coordinates, magnitude and angle, when frequency is varied from 0 to infinity. Okay, so we have to draw the polar plot. The polar plot in turn will be called Nyquist plot after certain transformation from some S domain to another delta domain, and this particular plot will be useful for the stability analysis of the closed loop system. Okay, so first we need to understand how to sketch this polar plot of frequency response. To sketch the polar plot of g of j omega, the entire range of frequency omega, that is 0 to infinity, is to be varied, and we need not to find each point of this varying frequency, but we need to understand 4 key points that usually need to be known. What are the 4 key points? Point number 1, the start of the plot where omega is equal to 0. So we need to find what is magnitude of g of j omega and what is the angle contributed by g of j omega at omega is equal to 0. Similarly, we want to find the end point of the plot where omega is equal to infinity. So once again we need to understand the magnitude and angle contributed by g of j omega at omega is equal to infinity. The polar plot will cut the real and imaginary axis. When it cuts the real axis, the imaginary part of g of j omega is equal to 0, and the polar plot will cut the imaginary axis, that is the real part of g of j omega is equal to 0, and these points we need to find, and this is to be done by rationalizing the transfer function, or there are some other methods as well. So we are going to see one of the method in the forthcoming video. Let us draw the polar plot of integrator, that is g of s is equal to 1 upon s. First step is to find out the sinusoidal transfer function. So we'll write g of j omega is 1 upon j omega, that is minus j by omega. The magnitude of this g of j omega is 1 upon omega, and the angle of g of j omega is minus of tan inverse of infinite, that is because it is a denominator term, it will contribute to negative angle, so minus 90 degrees will be contributed. So the first two steps is we have to find for omega tending to 0 what is the magnitude and angle. In this case, when omega is tending to 0, magnitude is infinite, angle is minus 90. When omega is tending to infinite, then magnitude is 0 and angle is minus 90. Angle is constant, minus 90 in this case. And when omega is 0, magnitude is infinite. When omega is infinite, magnitude is 0. Now let us understand how to draw it. Basically, this is the real and imaginary part of g of s. Okay, so let us understand how to take the angles. This is 0 degrees. Clockwise it is negative. So minus 90, minus 180, minus 270. Or we can go like this: 0, 90, 180, 270, 0. It is one and the same. So for omega is equal to 0, the magnitude is equal to infinite and angle is minus 90. Okay, so minus 90 is this angle. So at this particular value, the magnitude will become infinite as the plot will move towards omega is equal to 0. When omega is equal to infinity, the magnitude is 0, that is that origin, and angle is once again minus 90. So this plot will move with respect to increase in omega or reduction in omega rather, from omega is equal to infinite to omega is equal to 0 in this particular direction. So this plot, that is nothing but the plot of magnitude and angle of j omega with omega tending from 0 to infinity is called as the polar plot. Okay, so we can also show the direction of the polar plot with omega tending from 0 to infinity like this up to this particular origin value. Let us move to the next problem, that is the polar plot of the first order system. Let us consider this standard first order system. G of s is equal to 1 upon 1 plus st, where t is the time constant. Now representing this g of s in the frequency response form by substituting s is equal to j omega. G of j omega is nothing but 1 upon 1 plus j omega t. The magnitude of g of j omega is obtained as 1 upon square root of 1 plus omega square t square, and the phase angle is given by angle contributed by g of j omega is nothing but tan inverse of imaginary part by real part, that is tan inverse of j omega into capital T. Now at the start point of the plot, omega is equal to 0, right? So magnitude is equal to 1 because it is nothing but 1 upon 1 plus 0, and phase angle is also 0. When omega is equal to infinity, the magnitude is 0 and angle is minus 90 degree. But what is happening in the mid part of the plot when omega is equal to 1 upon t? When omega is equal to 1 upon t, in that case magnitude is 1 upon root 2 and angle contributed is minus 45 degrees because it is tan inverse of minus 1 by 1. The value of g of j omega at omega is equal to 0 and omega is equal to 1 upon t is shown in front of you. So for omega is equal to 0, magnitude is 1, angle is 90 degrees, and for omega is equal to 1 upon t, magnitude is 1 upon root 2, angle is minus 45 degree. If we tabulate in the table for omega is equal to 0, magnitude is 1 and angle is 0. For omega is equal to 1 by t, magnitude is 1 upon root 2, angle is minus 45 degrees. And for omega tending to infinity, the magnitude is 0 and angle is minus 90 degree. Now let us understand in the plot where are these angles. See, this is angle 0 and clockwise we take it as negative, anti-clockwise we take it as positive. So if it is 0, this will be minus 90, minus 180, minus 270, or it will be 0, 90, 180, thereafter 270 and like that. So here remember, what thing we have to remember is anti-clockwise is positive and clockwise is negative. So what is the magnitude when omega is infinity and what is the angle? The magnitude is 0 and angle is minus 90. So minus 90 is towards this direction. So plot will originate towards this direction, and the magnitude is 0, it is at origin. And what is the magnitude when omega is 0? When omega is 0, magnitude is 1 and it will start towards 0, right? So angle, it will tend towards 0. So 0 is in this direction. So the plot will go in this direction. But Here it is following a circle, semicircle rather. Okay, so we can also prove that this plot is following like a circle and its center is at zero point 0.5, radius is also 0.5, and with respect to change in the omega angle, this 1 upon square root of 1 plus omega square t square will act like a circle, semicircle rather. Okay, so this is the basically the polar plot of this particular transfer function, that is nothing but 1 upon 1 plus omega t. Now let us draw the polar plot of some second order system. Now let us consider the second order system. G of s is equal to 1 upon 1 plus st1, 1 plus st2, where t is nothing but the time constant, and we can represent once again this particular transfer function in sinusoidal transfer function by substituting s is equal to j omega. If we do that, in that case we can write down the sinusoidal transfer function like this. The magnitude of this g of j omega is given by 1 upon square root of 1 plus omega square t1 square root of 1 plus omega square t2 square, and the phase of g of j omega is denoted by phi is obtained as angle contributed is nothing but minus of tan inverse of omega t1 minus tan inverse of omega t2. And let us discuss the start point where omega is equal to 0. What is the magnitude? So magnitude when omega is equal to 0 is 1 upon square root of 1 plus 0, 1 plus 0, that is 1, and angle is 0. So it is represented here when omega is equal to 0, the magnitude is 1. This point is at 1. And the end point of the plot, omega is equal to infinity, magnitude is coming out to be 0, and angle is contributing to be minus 90, that is minus 180. So this is minus 180. So the plot will start from here and it will go, plot will start from here with omega is equal to 0 and it will terminate to origin. And here it is clear that the plot is cutting the imaginary axis, negative imaginary axis. So naturally we have to find out this particular value by rationalizing the transfer. Let us consider an example of polar plot of the transfer function. G of s is equal to 10 upon s into s plus 1 into s plus 5. So the first thing that we do, that in each case we represent this particular transfer function in sinusoidal form by replacing s is equal to j omega. So this is g of j omega. So first and second step is to find the magnitude and angle of this particular transfer function. Here the magnitude and angle relationship for g of j omega is written, that is 10 upon omega into square root of 1 plus omega square root of 25 plus omega square at angle minus 90 minus tan inverse omega minus tan inverse of 1 by 5 omega. And for omega tending to 0, the magnitude is nothing but infinite at angle of minus 90 degrees. At omega tending to infinite, magnitude is 0 at angle minus 270 degrees. So same thing is illustrated in point number 1 and 2, that omega is equal to 0, magnitude is infinite, omega is equal to 0, angle is minus 90 degrees. And for omega tending to infinite, magnitude is 0 and angle is minus 270. Let us see the point number 3, where the plot crosses the real axis. Okay, so whether the plot crosses the real axis or it does not crosses the real axis, it is quite evident that we have to rationalize the transfer function. So in this example we will do that. See, this is the transfer function, sinusoidal transfer function, that in turn we have simplified it in this way. And Rationalizing means multiplying the numerator and denominator by complex conjugate of the denominator term. So that in this particular case is after we solve this, it will come out to be minus 6 omega square plus j times 5 omega minus omega cube, and multiplying by complex conjugate term, that is minus 6 omega square minus of j into 5 omega minus omega cube divided by minus 6 omega square minus of, so multiplying the numerator and denominator by the same term. So in this way g of j omega is coming out to be like this, and for this term to be equal to 0, or we can also do by just equating this term to be equal to 0. So it is coming out to be, numerator part should be 0, and it is coming out to be 10 into 5 minus omega square is equal to 0. So omega square is equal to 5, omega is equal to root 5. Therefore, the intersection of the point between the polar axis and the real axis when omega is equal to root 5 is at, substitute g of j omega at omega is equal to root 5. So magnitude will come out to be minus 1 upon 3. Similarly, we can see the point where the phase plot crosses the, or polar plot crosses the imaginary axis. So for imaginary axis, the real part of that equation which we have found should be equal to 0. From here it is evident that omega is equal to infinity, and magnitude of j omega at omega is equal to infinity is 0. So this table summarizes what should be the nature of the polar plot. So for omega is equal to 0, magnitude should be infinite, angle should be minus 90. Okay, so minus 90 is basically this line. Okay, so magnitude will infinite means ultimately this plot will travel like this, like this, like this, and it will approach to minus 90 degree. When omega is infinity, magnitude is 0, angle is 270, so this is minus 270, magnitude is 0. So from minus 90 it will come like this, and it will approach to origin from this direction minus 270 degrees, and at the point where it will cross the real axis, that is this particular point, the magnitude is minus 1 upon 3, and it will cross the imaginary axis only at omega is equal to 0. So that is why this is the nature of the polar plot. Okay, so with this example, we have understood how to find out the entire polar plot of any particular transfer function. Let us see the polar plots of some typical transfer functions which are shown in the book of Katsuhiko Modern Control System, 5th edition by PHI. We already seen for this particular transfer function, that is integral term, the nature of polar plot is like this. For 1 plus j omega t by omega t, the nature of polar plot is like this. For the term s or differentiator, that is j omega, the polar plot is like this. 1 plus j omega t, the polar plot is like this, where it is starting from real 1 and approaching parallelly to the imaginary axis towards, positive imaginary axis towards infinity. For 1 upon s square term, the polar plot is naturally tending towards the minus 180 degree line. For j omega t by 1 plus j omega t, the polar plot is like this. We have seen for 1 upon 1 plus j omega t. So it was like this, and now it is like this. For the term 1 plus j omega t by 1 plus j omega at, where a is greater than 0, the plot is like this. And for this particular transfer function, the plot is coming out to be like this, and so on. Okay, so this is the way in which we can draw the polar plots, and I hope you have understood some idea of polar plot, and now you can solve the various problems in order to get rid of the fear of drawing polar plots. Let us understand basic concept of frequency domain, polar plot and Nyquist stability criteria. After learning this particular lecture video, you will be able to have a quick start of polar plot and Nyquist stability criteria. Now let us move to the next part of our syllabus, that is Nyquist stability criteria. But before we understand the Nyquist stability criteria, we have to understand some terms, that is enclosed and encircled. Okay, so let us consider this is a closed loop path, that we call it as a closed loop contour. So in this contour, let us consider 2 points A and B. We want to see whether the points A and B are enclosed inside or they are encircled. Okay, so the definition of enclosed and encircle is, if a point is lying inside the closed path, it is called as enclosed. If we traverse the particular curve in one direction, let us say the clockwise direction, and to the right of which the point is lying, in that case we call that particular point to be enclosed. For example, let us consider the point A and point B. Okay, so in order to know the number of encirclement, we draw a straight line from that particular point to any point on the curve, in this case S1. So the point A is not encircled by this particular closed loop path, but the point B is encircled because it is cutting this particular path. Okay, so the point A is enclosed but it is not encircled. Point B is enclosed as well as encircled. Conventionally, so this is nothing but the closed loop contour, which we represent it by this symbol. And we can also take the anti-clockwise direction. Traditionally, anti-clockwise direction is considered as a convention. So once again, if we traverse this particular path in the anti-clockwise direction, the point A is not encircled. Here the definition will be the all the portion which is lying on the left hand of the curve when we are traversing in the anti-clockwise direction. So the point A is not encircled, point B is encircled. So there is one encirclement and it don't have any encirclement. So this is what is the definition of encircled. Now let us consider a closed loop path. Okay. Now this is the S-plane, and in this we consider any arbitrary closed loop contour S. Okay. Let us say that there is one transfer function k upon S into S plus 1 S plus 2, and we represent it by delta of S. So we can map every points on this curve S1, S2, S3 into the another path in some other plane, that is nothing but delta plane. Okay, so this relation is onto relationship, that is for one value of S there is only one value of delta, but for one value of delta there are more than one values of S, there are three values of S. So this is called as onto relationship. So we can map this closed loop contour of S plane into the corresponding contour in delta of S plane. And the Nyquist stability criteria has originated basically from the principle of arguments. What the principle of argument states? Let delta of S be a single valued function that has finite number of poles in S plane. Suppose an arbitrary closed loop path is chosen in S plane so that the plane does not go through any of the points, poles and zeros of delta of S. The corresponding contour delta locus mapped in delta of S will encircle the origin as many times as the difference between number of zeros and poles that are encircled by the S plane contour S. Okay, so for system to be stable, the principle of argument states that the number of encirclements of the origin by delta of S-plane counter should be equal to number of zeros of delta of S encircled by the S-plane locus contour S in S-plane minus the number of poles of the delta of S encircled by S locus in S-plane. Okay, so once again I am telling you what is happening. We have considered the arbitrary closed loop contour in the S-plane. There are certain zeros and poles lying inside that. Thereafter we have drawn another contour, that is delta of S in some other plane, delta, and if the difference between the poles and zeros is equal to the number of encirclements about the origin, the system is stable. Okay, so if the number of encirclements is greater than 0, in that case the delta of S-plane locus will encircle the origin delta of S-plane n times in the same direction as that of the contour S. If n is 0, there won't be any encirclement about the origin, and if n is less than 0, then this contour which we have drawn in delta of S-plane will encircle the origin n times in opposite direction to as that of contour S. Okay, so this is what is called as principle of arguments. And what Nyquist has done, Nyquist has slightly changed this principle of argument, and he has come up with his idea, which we call it as Nyquist stability criteria, which is most successful in determining the stability of the closed loop system. So we are going to see that Nyquist stability criteria. Now let us consider these various closed loop contours. Here is the origin, and we draw a straight line from the origin towards the outer region of this closed loop contour. Here it is cutting 2 times, so number of encirclements about origin in delta of S-plane is -2, because conventionally we say that there should be counterclockwise encirclement. Here in this case there is a clockwise encirclement, that is why n is equal to -2. Here one clockwise encirclement, one anti-clockwise encirclement, that is why n is equal to 0. Here n is equal to 3, and in this case n is equal to 0. Okay, so this is why we calculate what are the number of encirclements in delta of S plane. Now the Nyquist stability criteria. Now the loop transfer function L of S, or what we call it as G of S, H of S, is having important role as it was there in root locus method. The characteristic equation we represent it by 1 plus GS HS is equal to 0. Here we represent delta of S is equal to 1 plus LS. LS is G of S, H of S. Right? So what Nyquist has done, the critical point which was circle in earlier case, he has shifted to the point -1 J0. Why? Because if this is equal to 0, 1 plus GSHS is equal to 0, then GSHS is equal to -1. So that is why the critical point which was origin is now -1 J0 in delta of S plane, and it becomes the critical point for determining the closed loop stability. Now what Nyquist has done, Nyquist has defined the Nyquist path that we are going to see in the next slide, and thereafter the Nyquist has stated his criteria that n is equal to z minus p, where n is the number of encirclements of -1 J0 point, and z is the number of zeros of 1 plus LSHS, that is nothing but the zeros of the closed loop transfer function that is lying inside the Nyquist path. Nyquist path is nothing but the polar plot of g of s h of s, and p is the number of poles of 1 plus ls that is inside the Nyquist plot. So whatever are the poles and zeros inside the Nyquist path, the number of encirclements about the -1 j0 point should be z minus p. Okay, then the system is stable. Okay. Another thing what Nyquist has done, that Nyquist for minimum phase systems, the Nyquist has defined the entire right half of the S-plane as path, that is Nyquist path. Okay, so what is Nyquist path? It is the entire right half where r is tending to infinite. Only thing it is not passing through the poles and zeros, poles rather, that are lying on the imaginary axis. So entire right half of S-plane, Nyquist has declared that it is Nyquist path. Now let us see for Nyquist stability criteria with minimum phase system. What is minimum phase system? A minimum phase system does not have the poles or zeros or roots of characteristic equation that are on the right hand side of the S-plane. Okay. And for minimum phase systems, m zeros and n poles excluding the poles at s is equal to 0. When s is equal to j omega, omega varies from infinity to 0, the total variation of L of s is n minus m pi by 2 radians. Okay, so let us consider the non-minimum systems. Minimum phase system is a system where the roots are not lying on the right hand side, and the poles or roots, they are on the imaginary axis. We are excluding it with the circle of infinitely small, that is very small circle, we are excluding those. Okay, so the number of encirclements in this particular case where the Nyquist has declared entire right half of the S-plane as Nyquist path, it should be equal to 0 because there should not be any encirclements, that is why n should be equal to 0. So the Nyquist stability criteria is stated as follows. For a closed loop system with loop transfer function L of s that is of minimum phase, the system is closed loop stable if the plot of L of s that corresponds to the Nyquist path does not encircle the critical point -1 j0 in L of s plane. For a closed loop system with the loop transfer function L of s that is of minimum phase type, the system is closed loop stable if L of s plot that corresponds to Nyquist path does not encircle the -1 j0 point. If -1 j0 point is enclosed by the Nyquist plot, the system is unstable. So this is the Nyquist stability criteria for minimum system when the system is stable, and this is the Nyquist stability criteria when the system is not stable. Okay, now this is what is the theory of Nyquist stability criteria. We can very easily identify whether the system is stable or it is not stable, and we will see one of the example to understand it properly. Let us consider the polar plot for the transfer function and let us check the stability of the system. Now g of s, h of s is 1 upon s into s plus 1. We can represent it into the sinusoidal transfer function, and we can find what is the magnitude and what is the angle. And once again we have to draw the Nyquist path of gh, that is nothing but polar plot in this case. So we have to draw the polar plot. For omega is equal to 0, magnitude is coming out to be infinity, angle is -90. So magnitude is coming out to be infinity. So this case, so it will, and angle is -90. And for omega is equal to infinity, magnitude is 0, angle is -180, that is like this one. Okay. And whether this plot will intersect the real or imaginary axis, that is not to be decided because it is first order system only. Okay, and this is the Nyquist plot, And what is Nyquist diagram? It is nothing but we are drawing the curve from 0 to infinity, so we have to draw another curve from minus infinity to 0, and it is simply the replica or mirror image of this plot around the real axis. So the entire closed loop curve is like this. It is this closed loop curve, and this closed loop curve does not encircles the minus 1 j0 point, therefore the system is stable. Because this is the minimum phase system, it do not have any right poles on the right half, and the closed loop path does not encircles the minus 1 j0 point. Okay, so this is the case. It is not encircling the minus 1 j0 point. That is why the system is stable.